Coaxial cable, or coax, is a transmission medium built for high-frequency signals. Its structure consists of four concentric layers. At the center is a thick, solid copper conductor that carries the data signal. Surrounding it is an insulating layer, usually plastic, that separates the center conductor from the outer shield. The outer shield is a layer of metal foil or braided mesh that serves as the return path for the signal and blocks external interference. Finally, a protective cable sheath covers everything. This concentric design gives coax two key advantages. First, it supports very high frequencies, up to about 1 GHz. Second, the outer shield makes it largely immune to EMI, electromagnetic interference, unlike twisted pair, which is highly susceptible. The thick center conductor supports high-frequency signals with much lower attenuation than twisted pair over the same distance. Today, coax is still widely used in cable television networks and the last-mile connection to homes, though in LANs it has been largely replaced by UTP Category 5 and 6 cables. One of the most important applications of coaxial cable is CATV, which stands for Community Antenna Television, or simply cable TV. CATV systems traditionally use coax to deliver signals at frequencies as high as 500 to 750 MHz over considerable distances. The total bandwidth is subdivided into 6 MHz channels, each carrying one analog television program. This is actually frequency division multiplexing in action, the same concept we learned earlier. Interactive CATV systems also include channels of various widths for two-way data and even voice transmission. Modern cable networks use a hybrid fiber coax architecture known as HFC. In HFC, fiber optic cables form the backbone carrying signals from the head end to neighborhood access points. From the access point to individual homes, coaxial cable covers the last mile. This hybrid approach combines the massive bandwidth of fiber with the existing coax infrastructure already installed in homes. HFC supports services like digital TV, high-speed internet, and voice-over-IP telephony, all delivered simultaneously over the same network. Cable internet using HFC typically provides speeds from 100 megabits per second up to 1 gigabit per second with DOCSIS 3.1. Let us compare the wire transmission media we have covered. Twisted pair is the cheapest and easiest to install, but it has the lowest bandwidth and highest susceptibility to interference. Its maximum data rate ranges from 100 megabits per second for Cat5 to 10 gigabits per second for Cat6a and Cat7. Typical reach is 100 meters for LAN and several kilometers for DSL in the local loop. Coaxial cable offers higher bandwidth up to 1 GHz with good EMI immunity thanks to its shielding, but it is more expensive and less flexible than twisted pair. It is primarily used for cable television and HFC internet access. Both twisted pair and coax are copper-based and share the fundamental limitation of signal attenuation over distance. In the next lecture group, we will explore wireless transmission, microwave links with their free space loss calculations, and technologies like MMDS, LMDS, and WLAN. Later, we will also cover satellite and fiber optic communications, completing our survey of all major transmission media. Let us review. Coaxial cable has four layers: center conductor, insulator, shield, and sheath. It supports frequencies up to 1 GHz and is largely immune to EMI. CATV uses coax with FDM, dividing the band into 6 MHz TV channels. HFC hybrid fiber coax combines fiber backbone with coax last mile, delivering TV, internet, and voice over one network. Cable internet via DOCSIS 3.1 now reaches 1 gigabit per second. Compared to twisted pair, coax offers higher bandwidth and better shielding, but at higher cost and lower flexibility. In the next lesson, we will enter the wireless domain with microwave system design and free space loss calculations.